Okay, let's get started. So welcome everybody to this session. My name is Patrick Eridita from ETH Zurich. So it's my pleasure to introduce the first speaker of this session, which is Bin Dong from Peking University, and he will tell us about learning to solve PDEs. Please.
Okay, all right. Thanks for the introduction, and also thanks for the organizers to putting up this workshop together and for inviting me to give a talk. In this talk, I will mainly talk about two different aspects. One is model reduction. It's a very new work jointly with my student and with my colleague. Well, she's an expert in Boltzmann equation. I'm just collaborating with her on the machine learning stuff. So but I'd like to hear some feedbacks for this. We did very simple 1D Boltzmann BGK, but we tried to use neural networks as the closure. So that's one work, and the other one is mostly on learning to solve a parametric PDEs by introducing this concept called meta learning. We had basically two different approaches. The one is using hypernetwork. The one is more like meta learning in machine learning, and trying to solve some elliptic problems and also Maxwell equations for electromagnetic simulations. So then I will conclude my talk and mention a few future works. Okay, so we know deep learning has changed the landscape of research for machine learning, artificial intelligence in general, and it has quite a few breakthroughs for the past few years. Well, its impact actually has spread way beyond the community of computer science. It has now had some impact on natural sciences, social science, and engineering as well. So for this talk, I will mainly focus on machine learning plus some aspect of scientific computing. Okay, so although deep learning has been successful for various tasks that we have heard of from the news or from from major journals and conferences, there are still many pending issues. And as I consider myself as a algorithm designer or practitioner, and I think some of the concerns are very important if we want to make machine learning that really works well in practice. The first one is related to optimization. We pretty much don't really know the inner workings of stochastic training. Why we have a way more number of parameters than the number of data, and why we don't see severe overfitting. At least for some, if you're training it well, then you don't see the severe overfitting. What's the implicit bias or the inductive bias caused by the network architecture? Okay, so that's one, and the other one is why it has this robustness issue, because when we do scientific computing in the past, we design algorithms that we want to make sure that the algorithm is robust. That's a must. That's a strong requirement. But for deep neural networks, it has fantastic accuracy, but the robustness is a major concern. That means if you perturb the data, maybe you perturb it on purpose, or the perturbation is inevitable. When you sample data from real world, that's the distribution comes from is different from the distribution that you use for the training. Then we want the model to be robust. And the third one is interpretability, and different people may have different interpretations on the word interpretability, but the interpretability I mean was that we want to create a model and that fit the observation data, and after fitting, we can actually learn something, extract some knowledge from the model that is fitted. Okay, so that's why that's why we did a few of my early works oriented such as PDNet, where we try to learn the underlying differential equations that approximately drives the observed dynamic data. Okay, so that's the interpretability that I think is very important. Okay, so a promising approach, at least our groups are focused most on empirical, but there are different various groups also focus also had some theoretical understanding is that so we should combine handcraft and data-driven models, or combine mathematical approaches and machine learning approaches so that we can find a good, a balance between, accuracy and robustness and interpretability. Okay, and I think I think optimal control is a very suitable framework for this task. So I'll just be a little bit more precise on the slides. Is that so? You can write down a general, stochastic, mean field version of stochastic optimal control into this form where the control is U, or maybe if the control is parameterized by some other theta. Okay, so the control is in fact just theta. So you want to steer the dynamics so that you have a ideal, terminal, minimize the terminal loss, and you have a minimized running cost as well. And how this is related to supervised learning, reinforced learning, and meta learning. Well, just imagine that you do a supervised learning task and you have your image inputted in your network, and the network is a certain discrete approximation, or you can interpret it in that way. It's a certain discrete approximation of a dynamic system. And in the end, and it outputs a latent space representation, and you try to understand the latent space representation and make a decision on whether it's a cat or dog image. Okay, and in the run, you can also minimize the running costs to reduce the complexity of of this entire dynamic system. And this is just a graph I plotted to illustrate this idea where you're doing a classification of two different clusters, and originally the data is intertwined, and after passing through the dynamics, that's the layer means time here, it's got disentangled, and in the end you can do just a simple linear classification, and that will just give you a pretty good classifier. And this dynamic observation was, I think, pioneered by Weinan's group, and also by Haber and Rufalto around 2017, 2016, and 17. And later we have two papers on ICML 2018 showing that, well, the discrete approximation of dynamic systems like ODEs and PDEs can induce a good neural architectures, okay, deep neural networks that can be so suitable for classification tasks in machine learning, or for inverse problems, both forward and inverse problems in scientific computing. Okay, so today I'll just follow. This is the general philosophy, but the catch here is how to pick a base dynamic system, and how to select the components in your F to be learnable, and which part needs to be learned from the data, and which part need not to be learned from data. We just design them, and how to make such a balance, and how to make such a design, and so that we can solve some scientific problems better than in the past. So that's the whole idea that I want to emphasize. And this framework is is very general, can include not only supervised learning, also model-based reinforced learning and meta learning as special examples as well. Okay, so let me start with the first work. It's a very recent work jointly with my student Zhengyi Li and from Peking University, and my colleagues Yanli Wang from Beijing. I think it's Beijing Center for Scientific Computing and Physics or something. It's a long name. And so we look at one. Well, this is the original Boltzmann equation. 3+3 dimensional Boltzmann equation. Computing this type of equation, the main challenge of computing this direct computation of it is mainly caused by the high dimensionality of this equation, right? You have this three-dimensional spatial and the three-dimensional microscopic velocity space. And computing this collision term, for example, if it's quadratic collision term, and you need to solve a five-dimensional integral, so that's a computationally involved. And there are quite a few, many numerical methods for solving Boltzmann types of equation. For example, the DSMC and also the DVM or spectral method, and also moment method. So here I label moment method because this is the method that we rely on, and we're trying to use neural networks to find a closure for the moment system. Okay, so in this work we focus on learning neural networks based on moment closure for 1D Boltzmann BGK, where means we're considering BGK collision rather than a more complex quadratic collision term. Okay, so what's the idea of a moment system? Because why do we want to learn the closure? Well, just consider this 1D Boltzmann BGK equation. and this M is the Maxwellian. So the moment closure, we follow the we follow the setting from this work, where we use an ansatz based on Hermite polynomial. Okay, this is the ansatz for F based on Hermite polynomial expansion, and we're trying to write out the equations for this for the coefficient F alpha. Okay, so that's the whole idea, and you can just keep on expanding this, but you need to stop at a finite moment M. Otherwise, you're going to have an infinite system. So when you stop, then you need to decide how you're going to close this M of M sub M F sub M plus 1, and using all the variables that rather than the next order moments, right? Otherwise, you're gonna keep on going forever. So you need to find an operator G, and that depends on all the earlier moments, okay, and also the Newton number here, okay, and so that well, the purpose is you want to decide what's the optimal closure function G, and so that this when you simulate it, it matches with for example with DVM, okay, the high accuracy but also high complexity methods, as close as possible. So that's the whole idea of doing this closure. Okay, so just a very brief review of, we have a lot of mathematical approaches for this closure. For example, you can just simply use 0, to fill out that void. Okay, or you can use many other different methods for the closure, and they enjoy different properties. For example, you can have global hyperbolic for the closed moment system, and there are quite a few machine learning based approaches already. I think it's pioneered by Jie-Qun Han and his colleague. I think it's the Winas group. They had a paper describing that we could use. I think they were even more ambitious. They said that, okay, we not only can use neural networks for the closure, we can also neural networks at the ansatz at the same time. Okay, so making this a nonlinear representation for the function F. Okay, and you can solve and many others as well. I will not go through them in details. Okay, so this is our design. So the idea is that we can use a neural networks, but not just any neural networks. We want this neural network to be able to preserve some invariances that we know classical method, like the ones that we had in the past, they automatically satisfy. Okay, if you do not enforce your neural network to have any special structures, and those invariances are not guaranteed to be satisfied. So we found that if you do have this invariances enforced, and your accuracy can be improved, and the generalization is actually better. Okay, so the invariances that we consider is Galini, but of course this is 1D, so you just need to make sure that it's translational invariant. So we mostly using convolution or convolution-like structures in the network, and also reflection and scaling invariances. So basically we do a little bit pre-processing and post-processing. Okay, and this is the this is the little black box that we have in here. Okay, pre-process and then post-process this little box, so that this G function, this is the neural closure that will satisfy the invariances that we wanted to satisfy. Okay, so this is strictly enforced. Okay, so that's basically the whole idea. So after we have that, we can solve the moment system and try to match the output with the data. So these are the losses, and this is the prediction generated by the moment system with this moment with this we call it IPNC. Invariance preserving neural closure, and compare it with DVM, the outputs by the DVM. Okay, so that we have this loss, and we can use this loss to train the parameters in here. Okay, so that's basically the idea. So we did a bunch of tests. I'll just mention a few of them. So we started with a combination of a smooth and a non-smooth initializations. We call it mixed, and the parameters in here, there are a lot of parameters in here. Okay, they're randomly generated, and we train the training set is generated by DVM for a certain a spatial range, and for a certain time range, it's from 0 to 0.1, and this is the same setting as the paper by Han and his colleagues. Okay, and this is the testing in comparison with Euler method with hyperbolic moment equation. This is the the classical approach. And this Herm MLC is the work proposed by in this work, and this is the IPNC is our work. And you can see that when Nussen number is high, and we have pretty clear advantage over the existing method, both classical and machine learning based method. And this is just to show that and also we can extrapolate in time t. And this is the statistics of the prediction error evolving with time t. Okay, and this is the accuracy. You see that you have this accuracy that is relatively uniform with respect to the Nussen number here. Okay, and this is for stopping time at t equals to 0.1. This is the stopping time for t equals to 0.2. Okay, the Nussen number goes from I think 10 to the -3 to 10. Okay, all right. And we also did, I think, the shock case. The shock structure case is pretty challenging, and we train it on the cases where the MA is the Mach number is smaller than 7. I think it's from 2 point something to 6. And then after training, we directly generalize. We can generalize it without retraining to as large as 21. And we had compared with HME and also with DVM. Okay, the other methods just crashed. So that's why we only compare with this two. Okay, they cannot evolve for such a long time. Okay, so this is for the MA equals 7, and this for MA equals to 21. Okay, so again, this is just a 1D, and it's served as us as a proof of concept where we can really use neural networks by enforcing some invariances, and we can improve the simulations. And now we're working on trying to solve higher dimensional Boltzmann equations with quadratic collisions. And now and in particular, we want to use neural networks to learn the boundary conditions. Okay, so that's one of the toughest problem for moment method of Boltzmann equations. Okay, so that's one. And I think I have 7 minutes, maybe. Okay, so let me quickly mention the other part of work, that is solving parametric PDEs. Okay, so what's a parametric PDEs? Well, that's when you have a partial differential equations where you have some parameters eta. Okay, that could be, for example, Darcy's law. Okay, we know this eta is the A of x. Okay, in the Darcy's law, and it could be the boundary conditions. It could also be the shapes of the boundary. Okay, so these are all hyperparameters. We want to create a solver that is relatively uniformly efficient for solving, a parametric PDEs. Okay, so that's one. We want it to be efficient solving parametric PDEs. And the second, if you can have a solver that is actually differentiable with respect to this parameters eta, then you can do a design. Okay, so that's why parametric PDEs is quite important in various fields, such like inverse problems and design optimization. Optimal control and etc. Okay, so this type of PDEs also always occur in this field. So that's why it's quite important. So we look at well, in the very first in the very first work, it's a joint work with my former PhD student Yu Yan and Professor Jinchao Xu from PSU. We try to improve multigrid method, solving a linear problem like this. Okay, so it's a discretization of equation that takes its form. It's an anisotropic steady state equilibrium diffusion equation. The classical multigrid method that actually doesn't the wall time increases as this epsilon decreases to 0. Okay, so it's getting harder to solve when epsilon goes to 0. So we do not assume that we know. We want the solver to be adaptive to epsilon and theta. Okay, and we don't want to just do meshing specifically for this anisotropic here. Okay, so how do we do that? So we just view solving a parametric PDE as a meta learning problem. Okay, or as a multitask learning problem. Where for each given eta, okay, it's solving this PDE for given eta is a task. So we can use meta learning to solve this this parametric PDEs. I think this is the perspective that we provided in this work. Okay, but there are different versions of meta learning. And in the work with jointly with Professor Xu, we use hypernetwork. So how do we use hypernetwork? So we started with multi-grid net, which was proposed earlier by Xu and He, and within this, one of the critical components in multi-grid is the smoother, right? And we introduced a hypernetwork. We called it meta neural networks, where it can adaptively decide which subspace to do subspace smoothing. It's adaptive to the residual R and also with respect to the operator A eta. Okay, so it's an entirely adaptive, smoother according to the problem that you have. Okay, and the design of the network is actually inspired by the Krylov subspace. So it takes this it looks a little bit strange, but it's just a generalization of the Krylov subspace method, and it has a guaranteed convergence for Poisson problem, but we do not know the speed of convergence because the speed of convergence depends on how well you train this network. That part, we don't know, but at least we know it's converges. And empirically, we show that for this type of problem, well, in our paper we have other examples as well, but for this type of problem, we can see comparing to multi-grid method, we have about approximately 7 times speed up. For the cases where epsilon is about 10 to the -5. Okay, and overall it's for the easy case it's comparable, but for the tough case it's much better than multi-grid. Okay, all right, and for the electromagnetic simulation, this is a joint work with Huawei, and in this project what we want to do is to speed up electromagnetic simulation so that we can do what we eventually wanted to provide a very efficient tool, to do all kinds of designs. Okay, for example, for the cell phone, or for chips, or for antenna. Okay, so the toughest part is, well, this is the normal pipeline, right? You have your CAD geometry, and you solve, well, you do meshing, and you solve the Maxwell equation, and then you look at the the scattering parameters, and to decide whether this is a good design or not. Okay, so this is the pipeline. The computation bottleneck is in here, right? For a complex geometry, you want to do meshing and you want to solve it, and it could be computationally expensive. So what we want to do is the first project is we want to be able to solve. So this is definitely a parametric PD because at least the shapes, the CADs can vary a lot. Okay, so we want to have a solver that can be solve this to solve this Maxwell equation with vary the geometry very efficiently. Okay, so we want to improve the numerical solver as much as possible, and also if we treat this entire step as a black box and try to establish a direct mapping from CAD to S parameters. If you do it this way, then we skip all the physics hidden behind it and try to establish a black box mapping between CAD and the S parameters. Okay, if you can do this properly, if you have enough data and if you train it properly, you can significantly speed up this process. So basically, we just try to do this, but there are a lot of challenges in terms of training and in terms of data as well. Okay, so for the for solving the parametric PDEs, we introduce a method we call it meta autodecoder. Okay, so it basically has 2 steps. The first step is to pre-train, given a set of hyperparameters. Okay, so this parameter is the parameter of the PDE, and we train a model. Okay, and when you have a new eta that comes, okay, so this is the new task, a new parameter, you want to solve it, and you can quickly adapt it. Okay, adapt the model from the pre-trained stage to facilitate the training or the solving of the PDE with a new parameter eta. Okay, and if you do not fine tune this theta, you just fine tune z, and this is done in earlier work. It's called a deep SDF. SDF means sign distance function, appeared on CVPR in 2019. Okay, and in this paper we give this whole approach, this a manifold learning perspective. So basically the manifold so the first step is trying to learn to approximate the solution manifold, okay, of all of the parametric PDEs. Okay, and after you fit the manifold and trying to solve for specific eta, is equal, you can view it as finding a coordinate z on the manifold that correspond to the specific parameter eta. Okay, and if you have more, eta comes in, and our vision is that, okay, so if you have more eta comes in, that means you have more task comes in. You need to first fine tune the manifold approximation, and then trying to find the coordinates z that correspond to the given parameter eta. Okay, so this is I think this is, as far as I know, this is a new vision on on solving parametric PDEs, and also I think on meta learning as well. Okay. So this is a comparison with existing meta learning approach, for example, Reptile, and it's one of the latest meta learning approaches, and with ours, and also with transfer learning, and also with comparing with the learning from the scratch. So if you're satisfied with with an error to the accuracy that's within 10% accuracy, and we have 20 times speed setup. So this 10% is, according to Huawei, it's already good enough. We do not want it to be more accurate than that. But if you look at this curve, it could get even more accurate than just simply 10 to the -1 relative error. Okay, and you have a significant speed up comparing to all other methods. Okay. And also, if you forget about solving PDEs and you try to establish a direct mapping from the CAD to the S parameters, you can speed up even further. Okay, within 10% error of the S parameters, you can have about 30% speed up. Okay, so this is a speed up over pin, and right now, comparing with very efficient implementations. Like the CST package, it's still, I think the speed is still comparable. Okay, we do not observe a significant speed up, according to this well optimized packages. But here, this is the real speed up if we can directly establish this mapping. But of course, the problem with this approach is that we need to have enough data, and we need to do pre-training properly, and also we need to build in some known knowledges into the network. Otherwise, you will see all kinds of overfitting. So this is still under development. Okay, and all of this are done by, I think this Huawei are trying to create this platform called MindSpore. I think it's equivalent to TensorFlow and PyTorch. So we're doing training on this architecture and using NPU. Okay. All right. So let me quickly wrap up. So that we have some time for questions. So basically we view deep learning as optimal control, and this actually grants a framework to combine learning and handcraft modeling. So as you can see that we're trying to embed learning in the classical algorithmic frameworks. Okay, for example, moment equations or multigrid method. We're only updating one or two of the key components. So the idea is you start with your favorite dynamics, for example, multigrid method, and you identify the component that is hard to handcraft. Okay, for example, we do not know exactly how to design a relationship between the hyperparameter eta and the smoother or the space that you want to do subspace correction. Okay, and you replace it by deep neural networks, and you pick up a loss function and you train it. Okay, but you can hope for the best, but prepare for the worst, because the training, as I said earlier, that it's one of the main challenge for deep learning. Okay, so well, I think the remaining challenge is from heuristic to theoretical, but of course for the computation itself, we're facing a lot of challenges as well. So there a lot need to be done. Okay, so with that, I will conclude my talk, and thanks for your attention.
Okay, thanks very much, Bim, for this interesting talk. So are there any questions? So are there questions in the room in Cambridge? Are there questions from the online audience? So if so, then you can just unmute yourself and ask the question. Yes, please.
Oh, okay. Nice talk, Dongbin.
Thanks.
One question is that in the part that you mentioned with the Huawei's collaboration, in the stage of a tune time, the tune this tune stage, when you have a new data come in, then you try to tune the parameters. How do you wait between the new data and the parameter you already got in a private step?
Well,
how to choose that? What you see that you have, seems that you have this sigma or something to weight how do you choose that parameter?
Right, we do not do, okay, so after the pre-training, all of the data are just gone. We do not use that. So in the fine-tuning stage, we only have this new ADA. That's just one, that's just one ADA that comes in. We have the equation, okay? We do not use the past ADA, we just use this one ADA, and all the training are memorized within this parameter theta. And and the only memory, that's one memory that we carry from the pre-training, and another memory carry from the pre-training is the Z. So we initialize the Z using this, using some of the ZIs that has a ADA that is actually close to the new task ADA. So other than that, we do not use the past data. So here, this is unsupervised. So I forgot to mention, this is unsupervised because we're actually using pin loss in here.
But how do you choose the sigma? The parameter in the sigma, is that something you have to choose, or?
Well, this is manually choosing. This is a hyper parameter that is manually choosing. Yeah. By trial and error, you choose one that works, generally as well. Yeah.
I see. Okay, thank you.
Thanks. Are there any other questions? Okay, then maybe let me ask a short philosophical question. So in the beginning of your presentation, you mentioned the reliability of these methods. And then at the very end, you said that you want to replace the physical structure by a black box, right? So when you learn these physical equations, so how do you make sure that the black box approach can be trusted in the end? So do you make sure that you train across all possible possibilities, or can you say something about this?
Okay. Well, that's an excellent question. So if you want to make sure that your black box that doesn't do anything crazy, you need to embed any known knowledge into the design of the network. That's what we did for the work on Boltzmann moment closure. Other than that, if you don't have it, you may have severe overfitting. So that's one way that you can overcome part of the overfitting issue. Or sometimes when you design this network, you can, so for example, you can use this network to have a component that is a operator that maps from the CD to a solution and then composed with a computation of these S parameters. And then this could serve as a network structure. We didn't do that, but I'm saying that if you want to make sure that this black box is trustworthy, then you should use a known dynamics with just a few learnable parameters to replace this black box. Okay, but if you do that, then you may not be able to get a satisfactory amount of speed up. So I think it's a trade-off between trustworthy and speed up. Yeah.
Okay, thank you. Are there any other questions? Okay, then many thanks to the speaker again. And then as I understand it, there is a photo shooting in Cambridge right now, and the next talk will be at 11:30.